Any questions from the last class? Yes. No. No. Okay. So in the last class, we saw that we were working in the interaction picture. So yeah. So we have this is probably the penultimate lecture, depending on how far I can get. And then let's see. So now what we want to do is we want to incorporate interactions. And we have been working in the interaction picture, which you will remember is defined this way. So this is a field in the interaction picture is written like this, but this is the, so if you have a Hamiltonian which has a free part and an interacting part, then this is the free part that goes here. And then we define and then we saw in the last class that the way the interacting the field in the interaction picture, which is phi it, evolves. So this is telling you that how the field in the interaction picture is related to the field in the Heisenberg or Schrödinger picture at a time t0. But if I focus purely on interaction picture, then the interaction picture field phi it is related to the interaction picture field at some other time t0 through this operator, which is u t t0. And this operator u t t0 was, we saw that it looks like this, where h0 is free Hamiltonian, h is the full Hamiltonian, including the interaction. And from here, if you take a derivative, you will find the following relation, where hi, remember, is the interacting part of the Hamiltonian written in the interaction picture. All of this is a little bit technical, but the final picture that we will have will be quite simple. Okay, so this is the interacting Hamiltonian written in the interaction picture, and that comes here. And we also saw in the last class that the solution to this has this form, where there is a time ordering appearing here. And we showed in the last class that without this time ordering, this exponential would not be a solution of this equation. You need this time ordering symbol to be here. You need this operator to be time ordered in order to ensure that this solves this equation. And in the last class, I had missed this factor of minus I over here, which should be there. Okay, so this is what we have as a recap. And again, any questions from this part?
So, in terms of time ordering,
Yes.
do we lose out on any information in terms of the mathematics?
Are we losing any information? No, I mean, we are not losing any information. Time ordering is just to ensure that sometimes there will be some ordering ambiguities, and time ordering take care of this. So it is about how to order. So when we have operators at different times, these operators need not commute with each other. So hi at time t prime and hi at some other time t double prime need not commute with each other. So we cannot move them. So if I have an expression like hi t naught, hi t double prime, this is not equal to hi t double prime, hi t naught. So I cannot move them left and right within an expression. What time ordering ensures is that everything is ordered. There is what time ordering ensures is that there is a correct order in which to place these operators. So if I have an expression, for example, if I didn't have this, I would have an expression where I have e to the power minus I h I t prime dt prime. If I expand this, I would get things like expanding the integral, I will have minus hi t prime dt prime. No problem here because it is just one integral, but then I have I square by 2 factorial dt prime dt double prime hi t prime hi t double prime, things like this. And here it becomes a issue as to which of these things should go first and which of these things should go second. There is no correct order, because if I write hi first, t prime first and hi t double prime next, that is different from writing hi t double prime first and hi t next. This time ordering ensures that there is a correct ordering in which to place these operators, and that ordering is that whichever happens. So if I have t prime greater than t double prime, then time ordering of these two operators is that I simply place the one that is at a greater time to the left. So this gives me an unambiguous prescription of how to place these operators, how to order these operators. Okay, and that is also the correct ordering which solves this equation. Okay, which we discussed in the last class. Okay, any other question? Okay, good. So let's continue.
Sir,
Yes, very
time
good.
ordering operator doesn't have any explicit form.
No, it does not have any explicit form. It just time ordering is just this. Time ordering of two operators phi x1 x2 simply orders them in time. It is phi x1, time ordered guy is phi x1 x2 if x1 naught, which is the time, is greater than x2 naught, and it is phi x2 phi x1 if x2 naught greater than x1 naught. That is the definition. And this is one kind of ordering. You had already seen another kind of ordering which also did not have any explicit form, which was the normal ordering, where if you had some operators a dagger, a, then you had to place all the a's to the right hand side. So this would be a dagger, a. This was normal ordering. This is time ordering. This is normal ordering. And in this class, we will see a relation between these two kinds of orderings. Okay, so here time ordering is naturally coming as the correct answer of finding this operator, how it evolves in time. So how the interaction picture field evolves in time, the answer is it evolves in time by acting with this operator. So if I want to have an interaction happening, something is interacting with something else, what I want to see is how the initial state is evolving in time to the final state. I want to calculate this guy, because this is telling me how it will evolve in time. So this is the important thing to calculate, because this has the information about how something evolves in time when there is an interaction. Okay, good. Okay, so now one problem is that so far we have worked with this, we have developed this free theory states P1, A, P dagger. This is what we defined. These are my states in the free theory. But these are eigenstates of the free Hamiltonian H naught. They are not eigenstates of the full Hamiltonian H. So these states that we discovered, they are not eigenstates of the full Hamiltonian. So they are not states in the interacting theory. So if I have a particle in the interacting theory, a particle should carry a fixed energy, and that particle should be an eigenstate of the full Hamiltonian. So a particle, so states of particles in the interacting theory are different from the states in the free theory, because these states are not eigenstates of the full Hamiltonian, only the free Hamiltonian. So the actual particle states would be, which we may call, say, Pi, would be some eigenstates of the full Hamiltonian. But we don't know what this is, because we cannot solve for the full Hamiltonian except in perturbation theory. So we don't know what these particle states are to begin with. So this makes our job difficult. How do we consider interactions involving these particle states when it is difficult to solve the equation for them? Because Klein-Gordon equation, free equation, was solvable. When I have an interaction term, it's a nonlinear differential equation which does not necessarily have a simple solution, or may not even have a solution. Okay. So what we do in perturbation theory is that, so this part is called scattering problem. We are considering an experiment where we suppose, so what kind of experiments would we consider? Suppose, we throw some things together, they interact, and then they again separate. I mean, if it was just, if we were throwing stones, for example, we would throw 2 stones, they would hit each other, and then they would go there a different way. Or if we have electrons, then we start the electrons with some speed. When they come close together, that's when they kind of start feeling their interaction, because for electrons, for example, their interaction dies off like 1 by r square. So when they're far away, they are not, if I have 2 electrons far away, they're not really influencing each other much. Only when they come close, when 1 by r square is, when r square is small, there's some interaction, and then they again go away from each other. So the situation we consider is that we suppose that initially the scattering particles are well separated. They are far away from each other, and they come. So suppose I have 3 particles coming in some 3 states, and then again they scatter, and then they go far away from each other. So some strange thing is, whatever is happening here, I am throwing in 3 particles from far enough away, and I am collecting again well separated particles. So then in the far past and far future, so this is the far past, beginning of experiment and end of experiment, when they have interacted and they have separated again, at this point we can assume that they are far enough apart such that they are not interacting. This is an assumption that we make to carry on with the theory, which is that when they are far enough apart, they are not interacting, or the interaction is small enough to be negligible. So in the far past, the interacting particle state approaches the free particle. The free particle is what we have defined from the free theory, and we assume that in the far past and in the far future, the interacting particles, which are the full Hamiltonian, the eigenstates of the full Hamiltonian, approach the eigenstates of the free Hamiltonian, because the interaction plays very little role. So for example, I mean, consider the example of throwing a particle. For example, if I were, let's say, gravity, throw a particle up with some momentum p, it has some trajectory and then it falls with the same momentum actually p. But in the far past, as I approach far past, I can see that this very early we could approximate this by a free particle with some momentum, some free particle momentum. Then it interacts with gravity, and at the end we can also think of this as a free particle with some momentum. Or you could think of an example where I start a free particle, throw a free particle, and then maybe at some point, I switch on gravity, and then it has some trajectory, and then after again, at some point I'm switching off gravity. Oh, okay. Partial. Then so let's say I switch on the interaction, whatever interaction is, switch on the interaction. Interaction is getting switched on when, let's say, 2 particles or particle and some field are close together, and then after a while they're far enough away, so I can think of the interaction being switched off, and then again it approaches some free particle. So the idea is I start with a free particle, they interact, and they go far enough away that again I can assume them to be free. So we will, so this is the picture we have where we call this some initial state psi, and then there is a state which I'm going to call psi in, and psi in is the state which asymptotically approaches psi. So psi is a state in the free theory and psi in is a state in the interacting theory, such that in the far past psi in approaches psi. So psi in is like this momentum which is changing due to interactions, but in the far past it approaches some free particle which we call psi. So the definition is at limit t goes to infinity, t goes to minus infinity, this psi in, which is evolving with the full Hamiltonian, its evolution looks like the evolution of some state psi 0 with the free Hamiltonian. So psi 0 is like the free particle, which is, so in the gravity example, psi 0 is like the free particle which I have thrown. There is no gravity, just like this. This is a free particle with no gravity. And in the far past, this guy also, this tangent also approaches that free particle with no gravity. So this is like your psi and this is like your psi in. So psi in evolving with the full Hamiltonian approaches in the far past. The time evolution looks like the time evolution of a free particle psi 0. And similarly there will be something for the far future also, and there we call it to be some out state. So some out state in the far future looking like this, psi 0, and some interacting state will approach that state in the far future, which I call psi out. So psi out is an interacting state and psi 0 is the free state. And again, when the interaction kind of stops, the interacting state approaches or begins to look like the free state. Okay. Any questions? Okay, so from this equation that I have written, I can rewrite this as e to the power I h t e to the minus I h naught t psi 0, and what is e to the power I h t, and this chi out is e to the power I h t e to the minus in the limit t goes to minus infinity, and this is in the limit t goes to infinity. Minus I h naught t. Now the problem we want to solve is that suppose I start with a field which is in the state psi in, and then what is the probability of it ending in some state chi out. This is the kind of problem we want to solve. We suppose psi in could be some state with some momentum p and chi out could be some state with some momentum p prime. So I give you an initial state, I give you a final state, and I want to ask that a question like this: what is the probability of, if I started with psi in, if my interacting state was psi in at time t is equal to 0, what is the probability that it, probability amplitude that it changes into chi out? And to solve this, I can use these formulae that I have written here. Now notice here that e to the power I h t to minus I h naught t is nothing but the time evolution in the interaction picture that we have written out here, right? It is this guy. and so we have this to be equal to 1 second, this is this was u dagger and this was u psi u dagger. So this is u dagger, this is a dagger of that. So this is u dagger t of 0, and this is also u dagger for in the limit t goes to minus infinity, and the other one is in the limit t goes to infinity, t is equal to 0. And now that there, when you write it like this, you get substituting. I have psi I have chi 0 u dagger t naught, and so this is, let me call it t1 naught. Okay, sorry, let it, because there are two limits. So limit t1 goes to infinity, t1 goes to infinity. I'm writing chi out now. Chi out is the t is equal to infinity chi. So this is chi 0 u t1 0, and this is t2 0. This is the other guy. T2 goes to, this is T2 goes to minus infinity, T2 0, and this is psi 0. And then you can show, which you will do in an exercise, that this simply becomes chi 0 u of infinity to minus infinity psi 0. Okay. So what does this result mean? So let me write it here again. Chi 0 u infinity minus infinity psi 0. What does this mean? So let me, meaning is that what I want to solve is a problem in the interacting theory, but I don't know the interacting states. So I assumed that in the far past and far future, interacting states look like free states. And then I showed that if I want to calculate the probability amplitude of transition from one interacting state to another interacting state, which were my chi out and psi in, the amplitude for transition between two interacting states, or two states in the interacting theory. That's what I mean by interacting states. Two states in the full interacting theory, that is the same as this equals chi 0 u infinity minus infinity psi 0. Now all of these things can be calculated in the free theory, where chi 0 psi 0 are states in the free theory. So I can start with states in the free theory and I can calculate their time evolution to some other state. All I have to figure out is this u infinity to minus infinity, which is the time evolution in the interaction picture from minus infinity time to infinity time. That is what I have to figure out. So in terms of a picture, I told you that particles in the interacting theory will be different from particles in the free theory. But we don't need to worry about particles in the interacting theory. If I am looking at a scattering, so I am at time t is equal to minus infinity, I am sending in say 2 particles k1, k2, and at t is equal to infinity, which means end of experiment, I am collecting 2 particles k3, k4. What I want is the probability amplitude in the interacting theory, but all I have to calculate is I have to consider this k3, k4 as particles in the free theory that we have already defined. We know how to define particles in the free theory. We have u infinity minus infinity here, and again we have particles in the free theory. So these are all in the free theory that we have already defined, meaning they are given by a dagger k acting on the vacuum, a k acting on the vacuum. Okay, so all of this exercise says that I can calculate the results of a scattering experiment, such as in the LHC, for example, from our free theory that we have developed. The only new thing that we need to calculate is this u infinity minus infinity. We can use the particle states that we have already defined. We don't need something new. We just need to calculate. We can relate this we can relate the interacting particles with the free particles by multiplying them with this u operators, and what we finally need is to calculate this u. Okay, so let me pause for questions. Now, should I explain this again? I think, yeah. Okay, let me say something. So what is actually happening physically in the real world? 2 particles coming in, let's say, interacting with each other and going away. Actually, how should I describe these particles? I should describe these particles as eigenstates of the full Hamiltonian, which includes a free part and an interacting part. This is hard to do. This is hard to do because it is hard to solve for particles for eigenstates of the full Hamiltonian. In fact, we cannot solve it. So what we can solve is eigenstates of the free Hamiltonian. This we can solve. This we cannot solve. Cannot solve. Can solve. But we realize that we don't need to solve this. It is enough to solve for the eigenstates of the free Hamiltonian, because the real particles, the particles in the real world, which are eigenstates of the full Hamiltonian, if I want to calculate, let's say k1, so I want to calculate something like the k3, k4, what is the probability that I do this experiment start with k1, k2, which is, let me call them full, because they are eigenstates of the full Hamiltonian, k3, k4 full. There is a relation which relates them to the eigenstates of the free Hamiltonian, which is something we can calculate, and we have calculated. So this is k3, k4 free, k1, k2 free. So we are mapping a problem that is we cannot solve to a problem that we can solve, and this is the u infinity minus infinity, where u t naught is given by time order d to the power minus. So this u infinity minus infinity is time ordering e to the power minus infinity to infinity I h of t dt. Okay. So we can map unsolvable problem to a solvable problem. All we need to calculate is this, and we need the assumption that at early enough times and at late enough times, the full eigenstates approach the free eigenstates because interaction is not happening. Okay, so this is the upshot of all the technical things that we said. Okay. Any other questions?
So this technique was introduced by Feynman or Dyson?
It's called Dyson's formula. Originally it was introduced, the first person to do it was Dirac himself, but Dyson formalized it, and then now this formula is called Dyson's formula. Okay. Okay, so one last thing, I think, at least one last thing we can do today is Wick's theorem. So you see that we have to calculate this u infinity minus infinity, which is something like this, and this Hamiltonian of course will be written in terms of fields, some phi x whatever, and then I will have to time order something that is a product of fields. But it is we know already how to. So okay, so suppose I have some Hamiltonian which is, let's say there are three fields, let us say, and the interacting Hamiltonian, let us say, is phi 1 x1, phi 3 x3, something like this. And each of these we can write in terms of their creation and annihilation operators. And so this thing is a product of many creation and annihilation operators. And we know such products are easiest to deal with in normal ordering, because then, you know, certain things cancel out, certain things go to zero. It's easier to deal with them. But what we have here is a time ordering. So it will be very convenient if we can find a relation between time ordering and normal ordering. And in fact, such a relation does exist, and it's called Wick's theorem. So I will simply write down Wick's theorem here, and then the proof is by induction, and it's not very illuminating, but you will do it in an exercise. But let me write it down. So if I have two fields, phi x1, phi x2, their time ordering and normal ordering are related by this. So this is time ordering, this is normal ordering, and this is some weird thing that I have written that I will explain. This line is called a contraction. So this line is called a contraction, but this is nothing scary or new. This is something you have already encountered. This is simply this quantity which we have seen before, the correlation function of 2 points, and we also gave this a name, the f minus xy, or the Feynman propagator. This name we gave it. We did not calculate it, which we will do in the next class, but this is what it means. Okay. So the rule is, I have time ordered thing, and it will be normal ordered plus a contraction, where you contract the fields at the 2 points. So this line is called a contraction. It is as if you are contracting the fields at 2 points, and this contraction is nothing but the 2-point correlation function. There are 2 points, so this is called a 2-point correlation function, or a 2-point function. For 4 points, it's very similar. So the first term is the normal ordered 4-point operator, and then you have to contract all the points. Okay. So the first thing is you contract. So you take any 2 points and you contract them. So suppose I take x1, x2, I contract them, and then x3, x4 normal order. And the next, now you have to take all possible permutations of this, all possible contractions. So what else can I take? I could have phi x1, x3 contracted, and normal order of the remaining 2, x2, x4. I could have phi x1, x4 contracted, and I have phi x2, x3. Anything else? I could have phi x2, x3 contracted, and I would have normal ordering of phi x1, phi x4, and I could have x4 contracted, and I would have normal order of phi x1, x3, and all of these are just these guys for various things. The most general thing, time ordering for n operators. First of all, I have n normal ordered, and then the first term will have two of them to be contracted. So phi 1, phi 2 contracted, phi 3, phi n normal order, and all other terms with one contraction, meaning two of these are contracted. And then I will have terms with two contractions like phi 1, phi 2, phi 3, phi 4 contracted, and then phi 5 to phi n normal order, plus all other terms with two contractions, and so on, etc. So 3 contractions, 4 contractions, 5 contractions, however many contractions you can accommodate within n, and then the rest of the terms will be normal order. Okay.
Is it possible that all the fields are contracted and none of them are?
Yes, so there will be one where all of them are contracted. I mean, if you have n is even, then you can contract all of them. Okay. Okay, good. So the last thing I want to say today is kind of going towards Feynman diagrams. So we take this. Okay, so now we know this is what we have to evaluate. This is our main thing. And suppose I take a Hamiltonian, so I will consider a particular example of a interaction Hamiltonian where I have 3 fields, phi 1, phi 2, phi 3. So the interaction, so the free part would be something like del mu phi 1 square minus m1 phi 1 square plus del mu phi 2 square plus m2 phi 2 square plus del mu phi 3 square plus m3 phi 3 square. 3 different fields, and the interaction is something that couples 3 fields together. So phi 1, phi 2, phi 3, and because it's in the interaction picture, I've written I here. So u infinity to minus infinity is, you get it by substituting this interaction picture Hamiltonian in this, and then I have a dt and I have a d3x. Together they become a d4x, integral over space time. I have time evolution, I have lambda, which is some constant which is small because we want to, this is called a coupling constant. Okay, and now the trick is to expand this and evaluate this order by order. So I expand this. The first term is this. I have already done this a few times, so you already know this. Phi 1, phi 2, phi 3, and then the next term is phi 1, phi 2, phi 3, and another phi 1, phi 2, phi 3. All of these are time orders. Okay, I am dropping the interaction suffix here. It is understood these are interaction fields. Okay, so what I wanted to show in this class is just a way of diagrammatically representing all these terms in the expansion. So phi 1, phi 2, phi 3, d4x, 3 fields, I write as, I have this one point x, and I write 3 lines corresponding to the 3 fields. So phi 1, phi 2, phi 3, 1, 2, 3, and x. And x is integrated over all space time. Okay, so there's a d4x here. So this is just a way to diagrammatically represent this term in the integral. This is not yet a Feynman diagram. We'll see Feynman diagrams in the next class. These are some pre-Feynman diagrams, you can say. Okay, and this becomes interesting in the next order. So now I have next order lambda square, 2 integrals. I have time ordering of this big term. Okay, so now I use Wick's theorem and I write this time ordering as normal ordering. Okay, so now you know that this, in this picture that you just saw here, that this Wick's theorem makes terms like you can categorize them by the number of contractions. So there's a 0 contraction term, 1, 2, 3. So the first term is one with 0 contraction. So this is I'm not contracting any of them. So then this I can represent by a picture where x1, x2, x3, this is x, 1, 2, 3, and this is y, and this is exactly like this term, 1, 2, 3. There is no contraction, so I have how did I call it? 1, 2, 3 here, and 1, 2, 3 here. Okay, so there is no contraction between any of them. So these are separate, whole thing is normal order. Now I have one contraction. So there are many ways I can contract two terms here, right? So I have phi 1x, phi 2x, phi 3x. Now of course I can only contract phi 1 with phi 1, phi 2 with phi 2, or phi 3 with phi 3, because those are the same fields. Because phi 1 and phi 2 commute, phi 2 and phi 3 commute, phi 1 and phi 1 doesn't commute. So phi 1x, phi 1y is some non-zero quantity, unlike phi 1x, phi 2y, which will just be 0. Okay. So what can I contract? I can, if I am considering one contraction, I can contract phi 1 with phi 1 over here, and the rest will be normal order. So I will have a term phi 1x, phi 1y contracted, and the rest are ordered phi 2x, phi 3x, phi 2y, phi 3. The way to represent them in a picture is just draw a line between x and y, and this mark this as 1 because phi 1 is contracted, and then I have 2, 3, 2, 3. Okay. So this is how we represent the various terms in the Wick's theorem. I start with this is the integral t. I expand this using Wick's theorem. I get all these terms in terms of contractions, and I have diagrammatic interpretation of all these terms by drawing pictures like this to make our life simple. So now I don't even need to write the terms to draw the next diagram, because you know the next diagram will be, the other two contractions will be 2, 1, 3 and 1, 2, 3, 1, 2. These will correspond to terms where I have phi 3x, phi 3y contracted, and the rest of the terms in normal order. This will this is my bad. This is this guy. Rest of the terms in normal order, and this corresponds to phi 2x, phi 2y, and the rest of the terms in normal order. And then two contractions. And again, I don't even need to draw the diagrams now, because I have x, I have y, and I'm telling you there are two contractions. Let's say 1 and 2 are contracted. So how would I draw them? I would draw two lines between x and y, and this leaves me with one line left. So I have 2, 3, let's say, and 1 is left. Or I can have 1, 2 contracted and 3 is left. Or I can have 1, 3 contracted and 2 is left. And so this corresponds to what? This corresponds to phi 2x, phi 2y contracted, and phi 3x, phi 3y contracted, and phi 1x, phi 1y normal ordered. So normal ordered things don't see each other. Contracted things are kind of giving you the interaction, telling you where the interaction is happening. Okay, and now 3 contractions, which is what Abbas was asking. All of them are contracted. So I have xy, and I will just draw 3 lines. 1, 2, 3, and this corresponds to phi 1x, phi 1y, phi 2x, phi 2y contracted, phi 3x, phi 3y contracted. Okay. So now we are seeing something more simple and intuitive in a way, as a way to represent this interaction, this interacting evolution operator in terms of these simple diagrams. And in the next class, we'll see what happens when particles are coming in and going out, and we'll get the Feynman diagrams. Okay, so I will stop here. If you have any questions, please ask.